talk about some of my recent research on domain-decomposition-based model reduction methods for linear convection-diffusion equations with random coefficients. So this is a joint work with my colleague Lin Mu at Oak Ridge. So she's a finite expert, so she helped me a lot on coding up and analyze those schemes and find out the correct way to do it, how to do it. So okay, so this is outline. So I'm going to introduce in the problem setting, I'm going to introduce the PDE. We're gonna solve and two specific examples, and next I'm gonna briefly overview the deterministic domain decomposition method. I mean, domain decomposition is a big area. I'm only going to introduce one of them, and which also helped us to set up all the notations that we need to discuss our methods. So I'm going to introduce our method and discuss it and how we set up the algorithm and why we do that, and in this section, and followed by the numerical examples, where I'm going to give like two examples. The first one is the diffusion equations with random diffusivity, and the second one is the convection-dominated problems with random velocity field. So then some concluding remarks. Okay, so this is the general formulation of the problem. We're interested in this steady-state linear convection-diffusion equations, where with the deterministic right-hand side and with Dirichlet boundary condition, and there's no randomness in right-hand side and the boundary condition. The randomness is in the coefficient, either the diffusivity or the velocity field. They both could be a random field. And of course, the well-posed is the standard. We impose some balance space, and we have this norm, and we guarantee the well-postness of the PDE. And the two specific examples. The first one is our favorite example is the elliptic PDE with the random coefficient. And this is the smooth problem we're going to solve, which will show the best performance of our method. And next, we're going to try to solve this convection-dominated equations with random velocities. This is the hard problem, and this is also a good example of problems with irregular behavior. Like we have this random velocity field, and the irregular behavior comes from the fact that we have this inhomogeneous boundary condition. The discontinuous along the boundary will set up some. I mean, because of this random velocity field, it will. I have an example on the next slide. So this is a specific example of this convection-dominated field, and with a very small diffusivity coefficient epsilon. Like here, this is to be 0.001. So. And we set the boundary conditions like this. So on the left boundary, from the middle to the bottom is 1, and the bottom boundary is 1, and all the others are 0. So if you solve that problem with a deterministic velocity field like this, like 0 and the cosine 0 and sine 0 is pointing to the right. So this is the solution we're going to get. And there is a sharp transition here, sharp transition layer here. And if we impose some random velocity field like this guy, and this is the truncated, for example, truncated KL expansion of color noise, and I plotted 3 snapshots of these solutions. You can see these 3 snapshots of this random velocity field. They're just these 3 realizations, and these are the 3 corresponding solution realizations. And you can see because of the randomness in the velocity field, and we have the same boundary condition, by the way. So the point is the sharp transition interface is moving, the location is changing. So if you use like a standard sparse approximation to approximate such function directly in the high-dimensional parameter space, you won't have a good sparsity, and I mean, this will make the problem very hard. So this is the problem we want to address in our talk, and I think this is interesting. Okay, so the standard, the random field of interest. So we're interested in 2 types of random field, and they can be written like in the same way in general. So it's like real valued square integral, and we have some probability space. We impose some space here, the L2 space here, and so in this space we can have inner product, which is the expectation and the variance of this. And for simplicity, we just assume the random field has mean 0. If you have another like profile of the mean, you can just add it in there. It's a deterministic, and has some covariance structure. So the true random field in the PDE, the diffusivity coefficient and the velocity could be just the functions, linear or nonlinear, of this random field. So specifically, the first one is the color noise and the KL expansion. This is, I don't need to introduce that too much because we are familiar with this. So, and we have this covariance structure, so we can decompose it, and we can decompose to have the set up the eigenspace, and we can represent this random field in the eigenspace. And all these random variables have zero mean, uncorrelated, and the variance is 1. So we can truncate this random field to do approximation, which is set up a finite dimensional problem. And here, I want to point out that for this expansion, the KL expansion, usually the Gaussian case is the most practical model because the non-correlation in the Gaussian case, means independence, which makes it very easy to sample. If you want to use some other distributions, you need to sample from an uncorrelated distribution. That's harder than the Gaussian case, at least. So, okay. And then the second one is I call it the discrete white noise because I want to say it's an independent random, piecewise independent, constant independent random field. So basically, we can decompose this spatial domain D, for example, into a non-overlapping subdomains Dn. This Wn means white noise, and they're non-overlapping. And each piece we put a random variable, and then it's similar to the inclusion problem in previous papers, but the difference is here we say we have a large number of these pieces, and they are all IID, independently identically distributed. So they have the same distribution. So basically, it's an isotropic problem. And the reason why we call it discrete is not true white noise because we don't assume our true solution has infinite resolution. So we just say, so our true random field has, for example, like 8 by 8 pieces. It's a 64-dimensional problem. That's it. That's the true solution. So because if it's like we want some infinite resolution, then the problem becomes harder. And also, it's a noise. It's not like the variance of this random variable. It's not like very big. If it's very big, then the variation is too high and it's discontinuous. It's hard to. We need to do something to use a better finite element solver to deal with that problem. So this is the two types of random fields we're interested in. And the brief overview of the deterministic domain decomposition method, how we solve those problems we're interested in. So first, we need to set up some finite element formulation. It's standard. This is the weak form, and for the elliptic problem, which is simple. For the convection-dominated problem, we need to add some stabilizers, and here we can see, at least in the numerical example, we use the streamline upwind Petrov-Galerkin SUPG scheme. For this, basically, it's just add an artificial diffusion in the velocity direction and along the interface. That's what it is to make it stable. And this is the standard expression of the solution in the finite element space, and those are since we're using the linear finite element space, so these are the coefficients are the nodal values of the solution. That's also important. Okay, so for the domain decomposition, first we need to decompose the domain, and we decompose the domain, the computational domain. We assume it's a box in 2D or 3D, and we decompose the domain into a set of open and non-overlapping subdomains. And then this is the computational domain D is the union of all these subdomains, and they're non-overlapping. And we use this notation to represent the collection of all the edges or interfaces like this for the domain decomposition. And this is an example of I divided this domain into a 3 by 3 subdomains. And important thing here is we want to align our domain decomposition with the finite element mesh, because all the interfaces are the edges, are the collection of the edges of the triangulation, so that we don't have those mismatch, which makes the computation very easy or much easier. And because of this alignment, so we have this, we can just restrict the finite element mesh within a subdomain and restrict the finite element space within the subdomain. Okay. So based on this domain partition for the deterministic domain decomposition, we can set up or write out the weak formulation within each subdomain. This weak formulation we restrict into each subdomain, and we can write out the local algebraic equation just for the the nodal values in the subdomain, and this system is singular because you don't have boundary conditions, so we cannot solve it. And the way the domain decomposition people handle it is they divided the components into US, which is the nodal values of the solution within the subdomain DS. So we divided the components of the in US into two groups. The first one is the US0. 0 means the interior unknowns, and the USBB means the unknowns on the interfaces. And then based on this regrouping, we can reorganize the algebraic equation or this matrix, stiffness matrix, into these 4 blocks. This is the A00 means it mapped the U0 to the interior, and the A0B maps the boundary unknowns to the interior, those kind of things. And we can also divide the right-hand side accordingly. And by doing that, and after that, we can set up apply the Schur complement to the local stiffness matrix, and to represent the interior unknowns by the unknowns on the boundary. And we can, and this is the BS is the Schur complement of the local stiffness matrix. And we can also do the same thing to the right-hand side, set up the right-hand side. And to solve this problem, we need to solve a global problem, solve all the unknowns on the interfaces first. So we need to set up like a global system. That's how we set it up. So we have this local Schur complements, and we just have this T matrix, which just the manipulation of the matrix to assemble a global system, to put the BS, all this local Schur complement into the correct locations in the global system, and we apply the T transposing the same thing to the right-hand side and also to the unknowns, and then we can set up a global system. And if we solve this one is a wild post. We solve this one first, and we get the unknowns on the interfaces, and then we supplement it into here, this representation, and we get for each subdomain. So we get the solution of the nodal values within each subdomain. That's how deterministic domain decomposition works. So here the hard part is this AS00 inverse, because if we want to do that, we need to either solve this, or we need to solve a linear system for every within every subdomain, which is costly. This is the heaviest cost in the whole process, because we don't want just invert A00 directly. So yeah, this is what I just said. So instead, what people would do is, because it's a linear problem, people can decompose the linear problem into a set of sub-problems with homogeneous boundary condition and the inhomogeneous boundary condition. And for each basis on the boundary within of each subdomain, we can solve a linear equation to kind of a set, and those solutions of these equations will contribute, each solution of this equation will contribute a column of this local stiffness matrix, so that we don't need to compute the A00 inverse to assemble this local BS, this local stiffness matrix, and then we assemble the global one to solve the equation. However, this procedure is very expensive, because the number of equations to solve is equal to the number of degrees of freedom on the interface for each subdomain. And if you have a very fine mesh, you need to solve many sub-problems for each subdomain. And this is only in the deterministic setting. If it's in the stochastic setting, what people would do is, in the stochastic setting, people do the domain decomposition following the same strategy. And people would do is they build a parameter approximation, or sparse approximation to the solution of this sub-equation. And they need to build sparse approximations to a large number of sub-solutions, local solutions, and which is it is also a very hard problem to do. And also, if you build approximations to the solution directly, if your solution has some irregular behavior, then you're going to lose sparsity, and then makes it even harder. So we are not going down that path. So which means we're not going to solve these equations so many times. This is one of the main contributions we have here. So here is in the stochastic setting, here is the overview of the current methods. So, for example, the motivation of using the domain decomposition is to exploit actually the structure, the low-dimensional structure of the local random fields to kind of overcome the curse of dimensionality in approximating this map from the parameter space to the solution. Because if you wanna, if you do a approximation from the subdomain and the parametric dimension dependence will be lower, so it's easier to set up approximation. And this is the incomplete list of these references. So for the polynomial chaos, domain decomposition for elliptic PDEs with color noise, there are several papers on this recently. And here, this paper is about the same setting, but with high contrast coefficient. It's like what I just talked about, the white noise, and with a very large variance each random variable. So, and here you need to use some like multi-scale Feynman scheme to solve it. And also it's also like there are some work on static condensation, which is another word for the domain decomposition or Schur complement. The reduced basis method for PDEs with affine coefficient and applied to like not in the random field case, but like a parametric PDEs with multiple components. And also there are some iterative UQ domain decomposition method for UQ, which is in another setting because they need to iterate along the boundaries, along the interfaces. They don't solve the global system once. They need to iterate. Okay, so this is now I'm talking about the objectives we have in this for our methods. So the first one is, as a model reduction method, we want to achieve an offline-online decomposition feature. So which means the offline computational cost is independent of the original Feynman mesh size. So no matter how fine the mesh is, they are all the online cost is independent. The online cost means when you use the reduced model to solve a problem, that cost is independent of H. And also the second goal is to handling high-dimensional non-affine random fields, like in the color noise case and the white noise case, for example, the log normal case. And the third one is what I just mentioned also, like we want to avoid the sparse approximation to the local PDE solutions, which is especially useful when the PDEs with irregular behavior, like the convection-dominated PDEs. Okay, so the first thing we need to do in our method is to decompose the random fields, and this is not new. This has been there for a long time. And in the KL expansion case, so we can expand do the KL expansion within a subdomain like the DS, and have some local expansion, and then we patch them together to assemble a global realization of a KL expansion. And the key thing is to when you do that, the key thing is to capture the correct correlation structure between for each realization between subdomains. So the way we do it is we first generate. We have a global KL expansion sitting above. We already have that. So we first generate a global realization, and then we use least squares to find the value of the local random variable which can match the realization of the global, the restriction of the global realization within each subdomain. That's how we do it to generate a global local expansion and capture the correlation structure among subdomains. And here is and this is based on the work to say, okay, the KL expansion, the eigenvalue decays faster as the ratio of the domain size over the correlation length decreases. So if the correlation length is small, if this ratio of the domain size and correlation length becomes smaller and smaller, so the KL eigenvalues decay faster and faster, which means we can return a very small number of dimensions to achieve a good accuracy. And this is the illustration. So we have this Gaussian correlation covariance function, and we have the correlation length to be 1, L equals to 1, L equals to 0.25. So, and we divide it into a 2x2 and 8x8 subdomains. We can see this is the eigenvalue decay, and the slowest one is the one with the global KL with the L equals to 0.25. And as we divide this global domain into more subdomains, the eigenvalues decays faster and faster, so we can have a smaller dimensional problem. And here, this on this side is, so remember we use the least squares, discrete least squares for each realization to find the correct parameter value for each local expansion. So we map from the global parameter value to the local parameter value using least squares. And here is the error between those realizations from the local expansion and the global expansion. Remember, this error comes from the fact that we truncate both expansions. If we don't truncate them, they should be exact. Because of the truncation, there will be error. And you can see the error also comes with the fact that if the correlation length is small, and if we divide it into smaller subdomains, and for the same truncation, we'll have a bigger error because we don't keep enough terms in the local expansion to achieve a good accuracy. So this is the kind of the motivation why we want to use the domain decomposition in the stochastic PDE setting. And this is for the color noise. And for the white noise, it's very simple because white noise is a piecewise constant function. We just do the domain decomposition, align the domain decomposition with the definition of the piecewise constant. That's it. So then they're going to be exact. Okay, so now I'm describing the offline procedure. For the offline procedure, which is the procedure to construct a reduced system or reduced model. So first, we generate training data. We sample the global KL expansion from a Gaussian distribution. We just assume it's a log normal random field. And we have this random field. And then we compute the realizations of the PDE solution. We have this number QU. We have this many realizations. And also, for each subdomain, we sample the local random variables. Here, we just, this is kind of this is an overkilling strategy, but we decided to sample it uniformly in the bounded cubic domain. Even it's Gaussian, but we decided to sample in the cubic domain for the realizations of the local KL expansion. And we just set the boundary to be big enough to cover the inscribed ball in the NS dimensional space. And the fact is that if the dimension is low, the difference between the volume difference between the inscribed ball or sphere and the cube is kind of small. If it's a very high dimension, you can't do that. But it's like a relatively low dimension, you can do this. And this will guarantee the accuracy because later on we're going to use some polynomial chaos to approximate this stiffness matrices. So for this local data, we don't collect the solution. Instead, we collect the samples of the local stiffness matrices. And I want to point it out that this sample is based on the local expansion, so it's not equal to the restriction of the global stiffness matrix within a subdomain because of the error between the global expansion and the local expansion. But it's for the color noise case. But for the white noise case, they are equal because we don't have errors from the local expansion, global expansion to local expansion for the piecewise white noise case. So this is how we generate the data. And now so to make the offline-online decomposition, we need to set up some reduced spaces. And then how we do it. We set up two types of reduced spaces. The first one is along the interfaces. For example, here we collect, remember we'll have all the data of noodle values, and we just collect the noodle values of all the snapshots on the surface, on the interface of the S subdomain, and we divided all the noodle values into ES groups. For example, this is the illustration. So we have 9 subdomains, and this D5 is example. So these are the noodle values on the interfaces. We divided into 8 non-overlapping subgroups, like say 4 corners and those each edge, and then we apply like a SVD to the snapshot to this each group, to the snapshot of each group on each interface. And this is, by this we can reduce the dimension of the degrees of freedom on the interfaces. And also the reason why we do SVD is because when we have a small enough subdomains, the dimension of the solution manifold on that interface is relatively low compared to a global solution manifold. So SVD will give us a pretty good approximation if we have enough number of samples. And this is the reduced basis for each group of the interfaces of each subdomain. This is the first reduced basis. And the second, and for these 8 groups, we can put them together to set up this diagonal block diagonal matrix, which is the reduced basis for the whole interface of the S subdomain. And then we can represent the unknowns by this using this reduced basis, and C is the coefficient. And this is the first reduced basis. And the second one is in the interior of each subdomain, we can also collect all the snapshots, and we do SVDs within each interior of the subdomain, and we set another reduced basis, and which is denoted by the V hat S0. 0 means interior. And also we can represent all the interior unknowns within each subdomain with using this reduced basis. And here we also use SVD. I'll talk about some other strategy later, but we haven't done that yet. But here we just use SVD, and it works pretty good. So, and now we need to reduce the cost, the online cost. We need to form some kind of reduced Schur complement using the reduced basis we have. For example, this is the original Schur the local stiffness matrix. We multiply. Here is the reduced basis in the interior of the S subdomain. Here is the reduced basis on the edges or the interfaces of the subdomain, and we multiply the local stiffness matrix from the left and from the right by this reduced basis, and we have this form. And using this form, we can apply the Schur complement to get the reduced Schur complement matrix, and also the reduced right-hand side, like this. And now we can assemble with those BS head. We can assemble a global reduced linear system to solve all the coefficients of the reduced basis on the boundaries of on the interfaces. And once we have that, we can represent for each subdomain. We can find out the coefficient of the reduced basis, which is the function of the coefficient of the reduced basis on the interfaces. We can have this coordinate. This is just the reduced version of the deterministic Schur complement system. And now, so far, we haven't talked about how to approximate the map from the parameter space to something. So if you look at this procedure, each of this reduced block is a function of the local random parameters. That's what we are going to approximate. So we want to construct sparse approximation to the entries of these 4 matrices, which are the functions of the local random variables. And the reason we do that, there are several reasons. And here we use, since we set up a bounded domain, and we just use the Lagrange basis to approximate that entry by entry for all the entries. The reason why I do that is because based on the model reduction of the reduced basis, the size of this reduced local stiffness matrix is independent of the finite element mesh size because of the reduction. And also because of the local KL expansion, we also reduce the dimension of this parametric dependence. So we reduce both the complicated part. In this case, we can reduce. This is the MSPLS is the cardinality of the sparse polynomial space. We can significantly reduce that number because of the local KL expansion, and we can reduce the number of entries or the functions we need to approximate. And so this is good, especially for the equations with non-affine coefficient. And in this case, if we can do this, we don't need to do empirical interpolation, and it will perform well, and because of the low dimensionality. So yeah, this is just a summary of what I just talked about. So because we do this, we don't need to approximate the solution map from the parameters to the solution, so we can avoid approximating irregular functions. Let me see. So for this sparse approximation to the matrices, So the reduced local stiffness matrices, we just use the anisotropic total degree polynomial space, which is not optimal, but it works because the dimension is low. We don't need to, I mean, you'll see in the numerical examples, we don't need to push too far to explore the sparsity. We also need to explore sparsity, but we don't need to use the most optimal strategy. And also other strategies can be used later if you want. So let me see. Yeah, those dependence of the local stiffness matrices on the parameters has no irregular dependence because in the convection-dominated case that we just showed, because the irregularity is from the boundary condition. And especially in the discrete white noise case, if we align the domain decomposition with the definition of the discrete white noise, and each local problem is just a 1D problem, which is much simpler to approximate. And the size of this local stiffness matrices are this, and the MS is the number of singular values we keep, is the dimension of the reduced spaces within each subdomain, like the interior subdomain, and the MSJ is the dimension of the reduced spaces for the jth group on the interfaces of the subdomain S. You know, both numbers are independent of the original finite element dimension, finite element mesh size, so which are good. So which means those matrices are small. Okay, this is the summary of the offline phase. So we generate the global KL expansion in the color noise. I use the color noise case as example, and we do the domain decomposition, and we compute the eigenvalue of the local KL expansion, and we generate training data, and generate reduced spaces on the interfaces, and assemble these reduced spaces, and we construct the reduced spaces for the interior unknowns within each subdomain, and we compute and store those things. Those things are needed to compute the right-hand side, which is also a small dimension because of this multiplication of these reduced spaces. And also we generate the training data for approximating the local stiffness matrices, and we construct the reduced spaces and the coefficient matrix for the least square approximation of this reduced local stiffness matrices. And this is the output. The output of this offline procedure is this least squares coefficient and those reduced spaces. That's it, and those vectors on the right-hand side. Okay, so yeah, I pretty much talked all of this already. So the dominant cost is the generation of all the snapshots of data, of course. And both numbers, this is the number of snapshot for the solution. This is the number of snapshot for the realizations of the local stiffness matrices. This could be reduced by dividing the domain D into more subdomains. But I want to point out that our method, the convergence of our method, does not require that the number of subdomains goes to infinity. So we just use the domain decomposition to reduce the dimension, but we don't rely on that number goes to infinity to get convergence. Yeah, so they are small, and the space requirement for the coefficient of this least squares approximation of the local stiffness matrix is also independent of the finite mesh size, which is also good. So we don't approximate a large number of quantities of interest in this case. So this is the online procedure. Since we have the offline procedure, and now we take those data from the offline procedure to apply to do the online procedure to solve or reduce the model for a new sample of the global KL expansion, for example. And we have this sample from the global, from a new realization of the random field, and we project those global samples to all the local random field samples, and then we evaluate the sparse approximation of all the entries of the local stiffness matrix, reduced local stiffness matrix at this sample, which is cheap. And now we compute the inverse directly of the A00, because this is possible because it's a reduced system, even it's dense, but it's easy to invert because the size is small. And we formulate the Schur complement within each subdomain. You can see all the matrices are reduced size, so they are all very fast to multiply. And we can also construct the right-hand side within each subdomain, And with all the reduced short complements, we can example the global reduced short complements. And also the right-hand side, we solve the global reduced system, find the coefficient of all the reduced spaces on the interfaces, and then we just substitute this guy into the short complement representation here. Since we already have the inversion, we can directly compute within each subdomain, directly compute all the coefficients of the reduced spaces within each subdomain to recover the whole solution. And this procedure is, you can see, this procedure is independent of the finite mesh size, which we want to achieve the offline-online decomposition. This is online. The complexity is independent of H. Okay. Now I'm going to show you some numerical examples. The first one is the diffusion problem with random diffusivity, and these are the KL expansion. Oh no, this is just a setup. This is the random field, which could be the KL expansion or the discrete white noise. And to approximate the local reduced stiffness matrix, we just set up the bounded domain, which is the -5 to 5, and the probability of having one sample fall outside this domain is like 10 to the -7. It's almost impossible. So we're good in this bounded domain. And the true finite solution is very fine. We have this fine mesh, this 2D problem, and the true solution we use the global KL expansion with the 200. We keep 200 terms to compute the true solution. And those are the singular value decay on one interface. Like we just want to show how the singular value decays on the interface and how the singular value decays within the subdomains for in different settings. For example, this is the correlation length equals to 1, and we have 2 by 2 subdomains, and we increase the number of subdomains and reduce the correlation length. We can see the fastest one is the one with the largest the fastest one is the one with the largest with the larger correlation length and the largest number of subdomains, and the slowest one is the one with the smaller correlation length and the smaller number of subdomains. So, and this is and we observe the similar things for the interior the SVD or reduced spaces approximation. So here is the error decay of the solution in the L2 norm with respect to different tuning parameters. This is the dimension of the KL expansion within each subdomain, and here, since we divided them into the subdomains, all the subdomains have the same shape, so we just say we use the same number for all the subdomains. And the second one is the number of singular values we keep on the interface. And the third one is the number of singular value we keep or the dimension of the reduced spaces within the interior of each subdomain. And this is the cardinality of the polynomial space we use to approximate the reduced linear stiffness matrices. And we can see the error decay. This is with respect to the local dimension, and this is for 2 settings or for 4 settings with the correlation length to 1, and we have 8 by 8 subdomains, and all the way to the correlation length to 0.25 with 16 by 16 subdomains. And the reason why it has a flat toe here is because the local KL error is dominating for these cases. So the way we generated this plot is we have the error computed at ns equals to 6 and equals to 5 and equals to 330 something, and this equals to 19. And for each of them, we just fix all the others at the largest number and decrease the variable that we want to plot. So that's how we got this, because so far we don't have a good error balancing strategy to make everything like a decay, to balance all the errors, to avoid all this flat toe. If you have a perfect a balancing strategy, we can avoid this flat toe. And you can see the error decay with respect to the singular values on interfaces is pretty good. Like for the elliptic problem, we can keep like 3 or 4 singular values, which can give us a good decay. And this is the number of singular values or the dimension of the reduced spaces within subdomains. And with 15 or even 19, we get, for each of the cases, we get good accuracy. And for the cardinality of the polynomial space 300 and something is good for the 6-dimensional problem. And in this case, we only need like about 1,000 realizations or the solutions of the PDE. This is because of the cardinality of this sparse approximation. And this is the cost. This is a little bit complicated to explain because we just use the CPU time to measure the cost. The way we do it is we say the relative cost, we say the denominator is the CPU time of one expensive finite solve, and we count the cost by how many expensive finite solves we require. And for the finite solve, we only count the final solve, the time for solving the final linear system using the / solver in the MATLAB, because you can use preconditioners or, I mean, there are a lot of solvers you can use, but this one, in terms of direct solver, this one is the most expensive, is one of the best solvers, and we just remove all the cost of assemble all those matrices because I believe our implementation is not the most efficient one. So, but this one is usually considered efficient. And the cost of KL expansion, this is offline, this is online. The cost of KL expansion, the cost of finite solves. You can see the number of expensive finite solves. If we have, this is the most expensive case. We have 2 to the 24th total degrees of freedom, and each solve is like take almost 400 seconds. And this is the offline cost, but the online cost, you can see if you multiply this number by the seconds, they are almost the same for different problems. So which means this is the online-offline decomposition. The online process does not depend on the finite mesh size. And this is the discrete white noise case. We have the same thing, and here we have 16, and this is the piecewise constant white noise independent Gaussian distribution. We have 1,000 realizations to do the SVD, but we only need 100 realizations for the least squares approximation for the local stiffness matrices because each of them is only 1D. We don't even need 100. We just need like maybe 20. That's enough, or 30. And here, since we don't have the KL expansion, I just plotted the decay with respect to the finite degrees of freedom. And this is the decay with respect to the dimension of the reduced spaces on interfaces, and this is the same thing with respect to the dimension of the reduced spaces in subdomains, and this is the cardinality. You can see in this case the cardinality decay is very fast because it's a 1D problem. We don't need like 6 or 7 orders to get a good accuracy. And this is for smooth problems, so the singular value decay is also pretty good. And this is the cost, I think, in the white noise case. It's similar result. The only difference here is the assembly cost, and then the cost of generating all the data for the stiffness matrices is much lower because we don't require that many. Okay, now the next one is the convection-dominated flow with random velocities. This is the example we showed before. Same setup with a random velocity field, and this is the same figure. I put it here. This is 3 snapshots, and here is the error decay. We can see this is the decay with respect to the local KL expansion, and we have 3 values for the diffusivity coefficient, and this one is they are like a 10 to the 0, which is 1, and 10 to the minus 2, and 10 to the minus 4. So the case of 10 to the minus 4 is the most convection-dominated case, which is the worst. We have the worst decay, we can see, but it's still pretty good in the fact that they have the relative error almost like 10 to the minus 4 in the 10 to the minus 4 on the order of 10 to the minus 4. And for the least squares approximation, we have the similar kind of decay. We can with about 350 degrees of freedom or cardinality, we have a pretty good approximation because of the dimension reduction based on the local KL expansion or domain decomposition. And we can see a difference between the convection-dominated case and the elliptic case is that the singular values decay is much slower, both on the boundaries or on the interfaces and within subdomains because of the sharp transitions. And the smaller the epsilon value is, the sharper the layer is, the slower the singular value decays. And we need to keep more singular values to get the accuracy, good accuracy. And this is the white noise, discrete white noise case, like for illustration, we plot 4 of them. This is 4 pieces. The white noise is 4-dimensional problem, and this is the 3 realizations. So we can see the interface moves, the transition layer moves. And here we have this error. We compute it in a similar way. So since it's only like 1D within each subdomain, so I want to say that the decay with respect to the cardinality of the polynomial approximation space is very fast, because you only need 3 or 4 orders to get to match and the slowest one is the decay with respect to the singular values on the interfaces and the one within subdomains, because that's the hard part for the sharp transition problem. So yeah, that's about it. So basically, in summary, we want to achieve like offline-online decomposition. That's our main goal in this work. And also we can handle like high-dimensional non-affine random coefficients, because we don't need any like empirical interpolation or the other strategies to separate the offline cost and the online cost. And we don't do the sparse approximations to the local PDE solutions, which is good for the convection-dominated problems. And now the future directions includes like so far we don't have any error analysis or error balancing strategies. So we want to set up that to better balance all the error sources. And so far the way we generate reduced spaces is through a SVD, but we want to incorporate the greedy procedures to generate reduced spaces in a more effective way. I don't know if it's feasible or if it's necessary, but at least this can give us a more optimal strategy in terms of the dimension, to reduce the dimension of the reduced spaces to achieve a good prescribed accuracy. And also, if you look at the whole algorithm, it's quite intrusive because we need to rewrite the code to do that. So one idea we want to promote in the future is to extend this kind of strategy to a non-intrusive algorithm, which does not require a modification of existing code. So this is the part of the things that we want to do, and also maybe extend it to the nonlinear PDE case. So in that case, we definitely need to introduce some iterative procedure, not just the simple Schur complement systems. And those are the main references. Yeah, and thanks for your attention.
Thank you. Are there any questions? Yep. The first question was going to be about errors, but I think it was on your list at the end. When you said you had no error balancing, did you mean that you can't just give an error tolerance and construct the reduced basis in such a way that it guarantees a certain error?
I can guarantee the accuracy, but I cannot guarantee the accuracy with the optimal parameter values. For example, if I want to hit this error, I can just say, okay, I keep like 35, it will give me a good one, but I don't know, this may be the optimal one that I should get. I don't have that strategy to find the best one.
People talk about reduced basis methods being certified or not.
Yeah.
Right, my question was really about the way that you build the approximation to the reduced matrices and subdomains.
Mm-hmm.
So you mentioned empirical interpolation, those people who do reduced basis, that's kind of a standard approach to doing that. So could you just comment on why you do it a bit differently? Is there
no empirical? Yeah, you can do empirical interpolation, but that's the extra work. And if you do the empirical interpolation in a global domain, the dimension is still high, the original dimension of the global KL expansion. So that's one part. If you're talking about the empirical interpolation.
I've not done it the way you've done it, so I'm just saying, what's the benefits? Why?
Oh, the benefit is we reduce the number of quantities of interest in or the dimensionality at the same time. We use the local KL expansion to reduce the dimensionality within each subdomain, and also we use the reduced spaces to reduce the size of the matrix. So the size of matrix is the number of the entries or the functions we need to approximate. We reduce both numbers. So that's the benefit. And hypothetically you can do empirical interpolation in the domain decomposition strategy without doing the interpolation we did you can do that, but that's the extra work. And we think this one works better because it's simpler and it gives us good accuracy. So, and for the empirical interpolation, you also need some other like a gradient strategy or some adaptive strategy to capture the manifold, you know. And yeah, that's kind of the motivation.
Any more questions? Yeah, I had a question actually. You always have sort of subdomains that are squares, so 16 by 16 and 8 by 8, and you get more accuracy as it gets higher. Are there any cases where you wouldn't have that square shape?
Yeah, I think as long as, I mean, for example, your PDE solver has to be well-posed. So I always assume I have a good well-posed working PDE solver in the first place for the geometry that you want me to handle. And then I have a triangulation, and I just align my domain decomposition, the interfaces with the triangulation. That's what I need to do. And if it's not squared, then you have to have different dimensions. Like you keep different dimensions in different subdomains, but that's fine. Yeah, that's fine. This is just simpler to implement. Yeah, this strategy.
I have perhaps a naive question, but I don't understand why, in the case of the KL expansion, it helps to do the domain decomposition. I mean, the eigenmodes of the KL expansion are global, right? It's not like they are wavelets with local support that promote the sparsity, localized sparsity of the action of the random variables, right? So why is that happening? I mean, you said you only need 5 random variables instead of 20 to describe the variability in each subdomain. But to me, again, I don't see why this is happening. If you need 20 random variables to describe the 90% of the variability, then you need it here and there and over there because they have global.
No, because if you decompose, if you do a KL expansion, you have a correlation length, and the decay rate of the eigenvalues or singular values depends on the ratio of your size of your domain over the correlation length. For example, if your domain is only 0.1, 0 to 0.1, and your correlation length is 5, then it must decay much faster than the case you have the other way around.
Yeah, but the basis is always global.
No, the basis is local too. This is the
Yeah,
point.
that's the point.
The basis is local. So local expansion, the basis is also local.
Okay.
That's why
there
is an indicator function to patch them together.
Okay, there was a misunderstanding.
Yeah.
I misunderstood. Okay, thanks.
Yeah.
So this is correcting what you said, that due to this domain partitioning, you reduce the correlation lengths in the covariance function, and therefore you have a faster eigenvalue decay for the random models on the subdomains.
Yeah.
But you still keep on the subdomain the same dimensionality as in the original problem, so the physical dimension of the subdomain is the same.
It's the same, yes.
Okay, but in this domain decomposition, at least in some of these methods, you decouple the subdomain, you can solve in parallel, but then on the skeleton you have to solve the global guy. But the skeleton has much fewer unknowns because the physical dimension is reduced by 1. So the skeleton.
Yeah. The skeleton. Yeah, the global. Yeah.
Of course, it is a complicated, but it's a finite product of interval. Okay.
Yeah.
So therefore, you benefit from the correlation length because you chop up this one. But in addition, if you do the KL on the skeleton, you also benefit from the lower dimension. Yeah. Because the KL eigenvalue by the while lemma, it will decay because you saw it in some of your plots. Yeah, actually, when you go to some of the plots, you will see exactly this effect. Yeah, if you go back, maybe here.
Yeah.
So there is an interface, and then
There's the interface.
Yeah. So of course it looks similar, but so when you compare the B and the C, and before it levels off. But what you see is that the singular value on the interface, check it there, it is a 1, 2, 3, 4, 5. It goes very fast. Yeah, it goes essentially like exponential to the minus the index.
Yeah.
But the other one in the C, it goes like exponential to minus the square root of the thing. square root because it's a
Yeah, it's a 2D domain. So
it's a
one,
volume,
right? Yeah.
so- and this, I believe, it is a big benefit. Yeah, that so your correlation length on the interface is also better because the interface is shorter.
You can just do a global expansion, but only take the unknowns on the interfaces.
Yeah. So then, because then you do it interface by interface, so the correlation length is this effect also on the interface. It is reduced, but on top, the dimension of the interface is one less than the volume.
Yeah.
So you have the e to the minus the thing rather than e to the minus the square root of the thing. So you have even more decay.
Yeah. Yeah, that's possible, but
So in this global problem, which you do obtain after condensing everything, you should have even lower dimension of the random components. If you solve only for on the skeleton, and then the higher one can be will be there, but it is in parallel by solving each volume by reversing the Schur condensation, which you described.
yeah, I agree. Yeah, so here in this work, we don't approximate the entire like a global system. We just approximate the local short complements and assemble to a global skeleton problem. So we don't need in this, at least in this strategy, we don't need a global map from a global KL expansion to the global like the skeleton system. We don't do that. That's kind of the reason why I didn't do that, because I didn't think of the just doing KL expansion on the edges. Yeah, on the skeleton.
I believe this could be because
this could be
a complete zoo of this domain decomposition. There is this Neumann, there is overlapping, non-overlapping, this one, that one. So you pick one of them. But I believe there is some other ones where then you, after you condense everything, you are stuck with a reduced compact global problem which only comes from the interface.
Yeah.
And that one will have both advantages. It will have a better correlation length because it is a product of shortcuts, plus it has lower dimensions as a faster decay.
I agree.
So it could maybe be even better.
Yeah, I agree.
Hey, David?
Can you just explain why you need SUPG?
Oh, because we need to stabilize the finite solver. Because that's the convection-dominated problem. We need some stabilizer.
Look, that convection dominated to me. What happens if you switch it off? What bit goes wrong?
Well, if you switch off, I mean, on the interview, you won't have a nice interface. Go to the very beginning. You won't have a nice interface. For example, you have like a sharp. I mean, if you plot like in the 3D, you have a sharp peaks, which cannot.
Square root epsilon interface. The square root epsilon interface. It's an interior layer. It's like a 30th or something. You can capture that on your mesh.
Well, probably, yeah.
But then you need to mesh refine.
Yeah, this is just a uniform mesh.
And then when you mesh refine, you have to do it because each sample gives a different one. So you have to each sample you have to remesh and capture the layer which is in a different. Because this is a sample.
Yeah, that's
so every time it is different font.
But this uniform mesh is fine enough to capture it.
Yeah, with the stabilization.
With the stabilization. This is with the
Without it, I suspect.
Well, what is the epsilon here?
10 to the
epsilon
minus
here
four.
is the 10 to the minus 3.
So
Yeah.
what is your mesh?
The mesh here, I think it's 512 to 512, 512 to 512.
Then
Yeah,
it's fine.
it's fine. It's fine enough, I think, for this case. Yeah.
Then it's
Yeah,
fine
this-
enough, So then it resolves.
Okay, so we'll finish there. And thank the speakers once again, please.
Thanks.
For all their